The circuit on your screen is that of a simplified common source amplifier. Other configurations exist too, each having their own merits, and we shall study them in due time. Right now we want to study how this configuration can be used as an amplifier and later on as a switch. Firstly, what's with the common in the name? If you see the figure, the source is common to both input and output. The source is also grounded, hence the name of the amplifier. The control action of the MOSFET is such that changes in the input voltage VGS produce changes in the current ID. However, the output can be taken to be a voltage simply by using a resistor RD as shown and taking the voltage of the drain terminal with reference to the ground. We now focus our attention towards finding the voltage transfer characteristic. That is the relation between input and output voltages. To do so, let us look at this figure first. This one is a graph that is probably familiar to you from previous lessons. The difference is that there is a bit more detail to it, and we are going to use this graph to derive the voltage transfer characteristic. These details I have included so that during the analysis you don't feel lost. You can pause the video and take a look at all these quantities on the graph and get familiarized with it. We are going to revise them as we go through the derivation of the transfer characteristic. So let's start. This figure is actually the Mosfet Id Vds characteristic curves for different values of VGS over which a straight line is superimposed, and this line is called the load line. This line intersects the VDS axis at VDD and has a slope of -1 over RD. Since RD is usually thought of as the load resistor of the amplifier, the straight line is known as the load line. This graphical construction can now be used to determine V0, which is equal to VDS, for each given value of Vi. Remember that Vi equals VGS. Also keep in mind the differentiation between instantaneous values and DC values. Remember, a V like this with a subscript like this is an instantaneous value, whereas a V like this with a subscript like this is a DC value. Keep those in mind and you won't feel lost. Now pay attention. For any given value of Vi or VGS, this part here, we locate the corresponding Id VDS curve, that is any of these curves, and find V0 from the point of intersection of the particular curve with the load line. If you're still confused, I hope when we start deriving, your confusion will go away. So just be patient. When Vi is less than Vt, the transistor will be cut off by definition, Id will be 0, and V0 equals VDS is going to be equal to VDD. We will be at point A. Agreed? You can see this on the graph on your right. Now as Vi exceeds Vt, the transistor turns on, Id increases, and V0 decreases. We are at this point. Do you agree that the voltage V0 is lesser here on this arrow than at VDD? On the voltage transfer characteristic, we can draw this like this. Since V0 will initially be high, the transistor will be operating in the saturation region. Remember the condition for saturation? VGD should be lesser than VT. This means when the drain voltage is much higher than the gate voltage, we will be in saturation. So, we increase Vi further and we move up the load line to Q. On the voltage transfer characteristic, we will reach the point Q as well. Now we move up the load line by further increasing the voltage Vi, and we notice that our output voltage continues to decrease. Now we reach point B. On the voltage transfer characteristic, we can also draw this. This, as you can see from the middle graph, is the boundary between triode and saturation. This is the point where V0 has decreased so much that it is now below Vi by Vt volts. At this point, Vi equals VIB. Now we increase Vi beyond VIB. We continue to go up the load line from B to C in the middle figure. In the corresponding voltage transfer characteristic, we can draw this by the segment BC, and when we reach the point C, the corresponding voltage at the output is going to be very small. Look here, this point, VOC. It is much smaller from where we started, VDD here. We can also see this on the voltage transfer characteristic. So what does this teach us? Let me identify three different regions on the voltage transfer characteristic: the triode, saturation, and cutoff region. Let me write down the cutoff region in the middle figure as well. From this graph, the voltage transfer characteristic, you can see that the nonlinear characteristic is almost linear between the segment A to B, this one. Hence, we are going to be using this part for amplifier. Why? Because the amplifier requires linear amplification, and this is an almost linear segment. We also see how the voltage transfer characteristic helps us understand how the MOSFET can be worked as a switch. When we want to keep the device off, we keep our input voltage lesser than Vt so that the device is in the cutoff range. So simply altering the input voltage, we can achieve functionality as a switch. Hope this topic is clear to you.